Good day, everyone. So our lesson for today would be about quantum mechanics, wherein we will be able to know how electron is viewed in quantum mechanics. Is it a particle or is it a wave? And you will also be able to know how the electron behaves in a particle or how the electron behaves inside an atom. You will also be able to learn about Heisenberg's uncertainty principle. So these new concepts are a lot different from classical mechanics. That's why it's modern physics, it's quantum mechanics. But I want you to unlearn first what you have learned before and then try to open up or open your minds to new ideas, because these things might actually shock you and you might even be confused after this lesson, okay? Alright, so let's start and let's squeeze your brain again, okay? Okay, so let's take a look at the history of the atom. Let's take a look at the different models of an atom. We have for John Dalton, he considered that an atom is a solid sphere model. And then for J.J. Thomson in your chemistry, we have this plum pudding model wherein electrons are scattered within the atom. Then you have here the nuclear model by Ernest Rutherford. And then of course we have Niels Bohr wherein there are different energy levels. And right now we are going to look into the new quantum model or the quantum model of an atom, wherein this was discovered by Erwin Schrödinger in 1926, okay? So this might be a very new concept for you, so let's try to understand this one. So I want you to look at this illustration. Before, we have considered, according to Niels Bohr, that atom has different energy levels, and that energy level or orbit is considered to be spherical or circular. But looking at this model of an atom, it is entirely different from that of Niels Bohr. So what's the difference? So you can see here that there's already a pattern, that electron is already considered as a wave. So that is a new concept for you, I think. If we are going to recall also, object's wavelength is inversely proportional to its mass. So if the mass is greater, that means the wavelength of the object is very small, that we can have it negligible or we can just neglect it. But if we are dealing with electron, wherein the mass is very, very, very small, then the wavelength would be large. So that means we cannot neglect the property of that electron having a wavelength or behaving as a wave. Now looking at this illustration we have here, electrons are considered to be both waves and particle. Now I will give you a link wherein it will be showing you an experiment, the double slit experiment, showing that electron is a wave or both wave and particle, okay? So I'll just give you the link on that. Now, if electron also behaves as a wave, so you can now see here the model of an electron. Electron is a circular standing wave surrounding the nucleus, or it's found in a circular standing wave surrounding the nucleus. So you can see here the waves. And any circular standing wave can only have an integer number of wavelengths. So it follows, you can now see the connection that energy is quantized. So that means there could be no energy within those energy levels. It is only a multiple integer of energy. The same thing with the wavelength. It can only have integer number of wavelengths. So nagkakatugma na yung konsepto of quantized energy and the number of wavelengths, which is also multiple integer. So you can see here also more wavelengths means more energy is carried by the wave. So if there are more wavelengths present, the energy will be greater. So it has a higher multiple of energy. So if you are also going to review Bohr's model of atom, so you have here N1, N2, and N3. So the greater the energy level, there are more wavelengths which can be found in that orbital or in that orbit wherein an electron can be found. So you can see here n equals 1, energy level or the ground level. Then you have n equals 2 and then you have n equals 3. That there could be no electron in between those energy levels because it can only possess energy within the multiple integers of the energy. Nothing in between. So you can see here also an illustration of quantization of energy. For example, you have an electron. It is found in a ground state. And then an energy or a photon hit the electron. So it will have that energy and then it will move to the next energy level. So it could be considered to be on an excited state. But once that electron moved down to the ground level or to the lower energy level, it will also emit an energy through photon, or it will emit photon or light. So again, let's take a look at the excitation in this illustration. A greater n value on the Bohr model corresponds to more wavelengths for the electron standing wave. So more energy level, higher energy level, that has resulted from more wavelengths or more number of wavelengths. Okay, so you can think of it as a standing wave. Since we have waves and optics also, you have a standing wave. Okay. So more standing waves will correspond to a higher energy level. Okay, so as I have mentioned, you have here the ground state. If there's a photon absorbed by or hitting the electron, it will have an energy so that it will be at an excited state. But no energy will be in between. So that means, considering that electron or the orbits, they are considered to be wavelengths, we can now consider covalent bonding. We can look into covalent bonding, or we can have a new look at a covalent bonding. So covalent bonding happens if there would be interference between those wavelengths. So again, from your optics, from your waves and optics, you have learned about interference, when there are two waves meeting each other, so we can have interference. So because of that, we can now have covalent bonds. So that could be another explanation of covalent bonds. Okay, next. I want you to look at this model. We now have here the nucleus, but surrounding it would be electron clouds. It is no longer a definite orbit. There's no defined boundary. You have nucleus inside, and then you have electron clouds, where the electron can be found. But there's no definite boundary of the electron clouds. But we have the different energy levels which are quantized. Okay, so I hope you are getting the concept of quantum model of an atom. Now looking at this is Schrodinger's equation to describe the wave function. So that is symbol psi. But of course, this is calculus based, so we will not look into the calculations of the Schrodinger equation, but we will deal with the concepts behind it. So according to Schrodinger, so this is his model, that there's an electron cloud surrounding the nucleus, but again, there's no definite boundary. So let's take a look at Born's interpretation. If the wave function of the particle has a value of psi, now psi is a function of x and time. So that means it's a function of position and time. So position and time can affect the wave function psi. The wave function tells us about the amplitude of the wave. But Schrodinger interpreted this one. If you have the wave function will represent a few electrons. But if we are going to deal with a number of electrons, if we are going to deal with greater number of electrons, then we will now consider the psi squared. So that means it's the probability of finding the particle between x and x plus dx. So that is proportional to psi squared dx. So according to Max Born, wave function is the probability amplitude, and the square of the wave function tells the probability that an electron can be found at a certain spot. So it's about probability now. We cannot really determine where the electron is, but it is probable or it's possible that the electron could be found in that particular spot. Okay, so that is Max Born and Schrödinger's interpretation of psi or wave function. Now looking at this equation, we have the intensity of the wave is directly proportional to the energy of the wave. And also the intensity is directly proportional to the energy, and it's also directly proportional to the number of photons. And eventually, or the next one is that the number of photons is also proportional to the strength of the electric field. So going back to the new concept about electron, or the new model of atom, it is electron would be found in clouds of probability density. So you can see there. Okay. Now let's take a look at this. If an electron could have both a precise position and momentum, it would be simply a particle. Now, our next topic would be about Heisenberg's uncertainty principle. But what does it mean? If, for example, you're looking for a ping pong ball, for example, brown out, then you're looking for a lost ping pong ball. Once you touch the ping pong ball, you were able to identify where it's located. However, you can give that ping pong ball a momentum so that it can actually move. And then the next thing that could happen is that you will not be able to find it again. And then you look for it. Once you identify the position again, but you give it a momentum, you will not be able to know the future position of that object. So, just like Heisenberg's uncertainty principle. So if you can recall, in kinematics or in classical physics, in mechanics, once you know the force, you know the initial position, you know the mass, you can actually define or identify where it will be located for a particular time, let's say 5 seconds. You will be able to compute where the object will be located, but not in quantum mechanics. So the difference would be, quantum systems are not deterministic, unlike classical physics, wherein we can determine the future of the particle. But quantum mechanics, it's about the probability. So it's the probability that the electron might be there. It is also possible that the electron is not there. So if quantum system, it's probabilistic in nature, so how do we describe the position and momentum? Take note that the inaccuracy in defining or in being able to define both the position and momentum, it's not just about the measuring materials that we are using, but it is actually inherent in nature. Okay, that probabilistic nature of quantum systems. So now, how do we describe position and momentum? We have Werner Heisenberg to describe the relationship between position and momentum, or we have here the Heisenberg's uncertainty principle. The Heisenberg's uncertainty principle for momentum and position is defined as this one. Delta x, which is the uncertainty in position, delta p, which is the uncertainty in momentum, must be greater than or equal to the reduced Planck's constant divided by 2. Okay, I'll show you some equations later about this. So let's look at the concepts behind this. That means if you can identify the position of the electron, you will be uncertain about its momentum. But if you will be able to define the momentum or the change in momentum of the electron, you will be uncertain about the change in the position. So that is Heisenberg's uncertainty principle. Okay?